Hey class, this is going to be your 7.2 video. So 7.2 is just to bring you up to speed on matrices in case it's been a minute or 10. So a matrix is any rectangular array of numbers. We're mainly going to be dealing with square matrices, but they come in all sorts of varieties. When we talk about a matrix, we talk about its number of rows first, and then its number of columns. So this is a 2 by 3 matrix. It has 2 rows and 3 columns. That's a 2 by 2 matrix. Honestly, that's what we're going to be dealing with the most in here. Every square matrix has a determinant. A determinant is some measure of the matrix, and for a 2 by 2 matrix, we actually do this by multiplying on the main diagonal, multiplying on the other diagonal, and doing a subtraction of those two numbers. So 1 times 4 minus 3 times 2 is negative 2. Notationally speaking, we say that this is, again, rows first. So Aij is the thing in row I, column J. So this is A1, 2. In row 1, column 2 is the number 2. Let's see, what else was I going to tell you about? This was just a formula for finding which number was here. Don't worry about that. That's silliness. So if we have a matrix, then we can transpose the matrix by switching your rows and columns. So for instance, the transpose of that matrix, so A is the matrix 1, 2, 3, 4. A transpose is going to be 1, 3, 2, 4. We just switch the rows and the columns. So the row there was 1, 2, now it's a column. The row was 3, 4, now it's a column. A bar is the conjugate, that's the complex conjugate, so that's not going to change a matrix with all real values, but if you have a matrix with complex values, then we might take the conjugate of every element. And then the conjugate transpose is sometimes called the adjoint of A. Technically, there's like 2 or 3 different kinds of adjoint, so some books and some instructors will just call this the conjugate transpose so that there's no confusion. But you just take the transpose and the conjugate. So let's see if I can get that all on the screen there. There you go. So here we had a complex valued matrix 3, 1 plus I, 1 minus I, negative 2. Here's the transpose. All we did was switch the row to be a column, switch the row to be a column. Here's the complex conjugate. All we did is switch the signs on the imaginary parts. So that was 1 plus I, now it's 1 minus I. This was 1 minus I, now it's 1 plus I. So then this matrix, when we take the conjugate transpose, or just the adjoint, the main diagonal is going to stay the same, but we get the same matrix as the original, and that kind of matrix is called self-adjoint. So if A is its own transpose, it's called a symmetric matrix. It's symmetric along that main diagonal. But if A is equal to its own adjoint, then it's called self-adjoint or Hermitian. I'll stick with self-adjoint. Again, this is a review, so I'm going to run through this kind of fast. If you have any questions, shoot me an email. So you add and subtract 2 matrices. It's important that they have the same number of rows and columns in order to do this, but you do it just by adding and subtracting the like positions. So this position plus that position plus that position, and so on. We can multiply a matrix by a scalar. If the scalar is on the outside, it's the same as multiplying every position in the matrix by that scalar. If we want to multiply two matrices together, it's easy if they're square matrices. You just are going to multiply the first row by the first column, and that goes in the first position, and then repeat. So the first row times the second column would go in the 1, 2 position. This is just a formula that says how to do that, but really, if to find this guy, that's the second row, second column, I multiply the second row by the second column. That's how you'd multiply two matrices together. A few problems here. So we've got A is 1, 2, 3, 4, B is 5, 6, 7, 8. A minus 2B, so we would multiply B by 2, and we would subtract each position from A. So for instance, 1 minus 2 times 5 is negative 9. 2 minus 2 times 6 is negative 10, and so on. I am not going to work all of these for you. You see the little note there says to have you work them, so feel free to pause the video and make sure you can get all 4 of these by doing those. All right. Get that all on the screen here. So, properties of matrices. Addition is commutative. You can do it in either order, no problem. Matrix multiplication has a distributive property. We have to be careful though, because AB is not equal to BA. You see that down here. So if we're talking about multiplication by A on the left, we need to make sure we bring it in on the left. And matrix multiplication is associative. So those are some of our standard properties that we look for, and we get those, but we do not get commutative multiplication. Try one. Take this one and, well, here, we just did it up here actually. C was A times B and D was B times A, and you see these are different matrices. All right. One of the most important matrices that we have is the identity matrix. The identity matrix basically replaces 1 in the world of matrices when we're talking about multiplication. So multiplying a matrix by the appropriate identity matrix gives you that same matrix back. So for instance here, let's just do 1, 2, 3, 4 times the 2 by 2 identity matrix. So first row times first column is 1. First row times second column is 2. Second row times first column is 3. And I think you can see why this works. And that's true for any square matrix. But it's also true for some the non-square matrices. It's just so long as the matrix multiplication has been defined. Now we only defined it here for square matrices because this isn't a linear algebra class, but that's the idea. So another important thing to consider for matrices is whether or not they have an inverse. That is, if A times something is the identity matrix and that same thing times A is the identity matrix, then A is invertible. We also call it non-singular. You don't have to worry about that. Invertible is fine. And then B is called the inverse of A, and we normally write that as A to the negative 1 power, or just call it A inverse. A matrix without an inverse is called singular, or you can just say non-invertible, either way. And a quick test to see if a matrix is singular is to check its determinant. Matrices, square matrices with 0 determinant are not invertible, and if they have non-zero determinant, they are invertible. So this is for us a little bit like, remember, we've been checking the Wronskian to decide whether two functions were linearly independent. And so we're used to checking a determinant to see if a property holds or not. And in fact, these are related. We do have a formula for the inverse of a 2 by 2 matrix. So if we take 1 divided by the determinant of the matrix, see why it can't be 0. And then we switch these positions and we negate those positions. Then we can compute the inverse that way. We can also do it by row reduction. If you guys have used row reduction, you go for it. So here we go. We can find the inverse by using row operations. We can use the cofactor formula, which is basically this guy's big brother. He works for other matrices. And yeah, many calculators will compute an inverse. You guys are going to be taking this next test on, at home. And I don't mind, for the purpose of this, if you use computer algebra software, use Wolfram Alpha or something to compute a matrix inverse. If it was a linear algebra class, I'd want you to be able to do your matrix operations by hand, but I'm really more worried about the differential equations in this class. So feel free to use those any way you like. So let's see if we can compute the inverse of 1, 2, 3, 4. Well, I guess we can, because I revealed too much at once. But if we take the determinant of this, we know it's -2, so it does have an inverse. And so the determinant of this is going to be 1 over -2 times 4, 1, -2, -3. And then when I just multiply those in, I get -2, 1, 3/2, -1/2. So that's how we get this right here. Oh, you can't see that, sorry. It was 1 over the determinant of A, and then we switch these two, so that's the 4 and the 1, and we negate those two, and then I just multiplied in the -1/2 to get this. You can already see the answer. Here B is singular. 6 minus 6 is 0. Its determinant is 0, so B, we can't find an inverse for it. All right, a few more things here. If I have a matrix, I can take the derivative of if the matrix, has functions inside of it, I can take the derivative of the matrix, and I just do that by taking the derivative of every position. I can also take the integral of a matrix by taking the integral of every position. So I've got A is t1, 3t, t squared, and I want to find A prime of t. So A prime of t just simply is 1, 0, 3, 2t, just taking the derivative of each of those. And the integral from 0 to 1 of A of t dt is equal to, well, the integral from 0 to 1 of t is going to be 1/2, right? It's 1/2 t squared, and then you substitute in the 1 and the 0, and that goes away. That'll be t, that'll be 1 minus 0, so that'll be 1. This will be 3/2, and that will be 1/3 t cubed, so that'll just be 1/3. Some derivative rules here. The constant just comes right out. Comes right out of the derivative. It comes right out of the matrix. We can pass it in and out. Same for the sum. We can pass the sum in and out. And so long as this product is defined, we get a product rule for our derivatives that is the same as the regular Calc 1 product rule. All right, so then if I have this x, and I want to verify that it's a solution of x prime equals this matrix times x plus this vector, then what I really need to know is, well, what is x prime? And I apparently didn't grab that sheet, so let's just work it right here. So x prime is equal to 1, 0, e to the t, because this is a constant vector, plus 2 times 1, 1. If you've only done Calc 3 vectors, these are equivalent to this, except we care about this being in a column form. But otherwise, it's just a constant vector. So the 2, 1, 1, those are all constants. And then that's e to the t plus t e to the t. So now we want to put this in this form if we can. So notice that this is equal to 1, 0, e to the t plus 2 times 1, 1, e to the t plus 2 times 1, 1 t e to the t. And this plus that is my x. Hold on, that's not what we were trying to show. So let's just hold on to that for a second. Go ahead and just keep track of this. We're going to also compute this. So I need to compute 2, -1, 3, -2 times x plus 1, -1, e to the t. So how does that work? Well, it works by me getting another piece of paper. Give me just a second, guys. I just don't have enough room on that paper to show you. So 2, -1, 3, -2 times x is 1, 0, e to the t plus 2, 1, 1 t e to the t, right? I've got to look back at that previous page to make sure. Yeah. So this is equal to 2, -1, 3, -2 times 1, 0, e to the t plus, I'm going to go ahead and move my constant out front, 2, -1, 3, -2 times 1, 1, t e to the t. So we only define matrix multiplication for square matrices, but it still works for a matrix times a vector. So first row times first column is going to give me 2, and second row times first column is going to give me 3. So that's 2, 3 e to the t plus this one is going to be 2 times, that'll be 2 minus 1, so that's 1, and that'll be 3 minus 2, so that's 1, t e to the t. Now, I just got rid of that other piece of paper. Here it is. So we have on the one hand that x prime equals 1, 0, e to the t plus 2, 1, 1 e to the t plus 2, 1, 1 t e to the t. And on the other hand, we know that this matrix times x is equal to that. So let's see what we have here. So this is equal to, if I add this up, that's going to be 1 plus 2 times 1, that's 3, and 0 plus 2 times 1 is 2, 3, 2, e to the t plus 2, 1, 1, t e to the t. I think that worked out. I've honestly lost track of everything we were supposed to do. Oh no, these aren't quite equal here. There we go. That's the missing piece. So x prime is equal to this. This is, I'm going to call that ax. But we were looking for, so this is ax. Here's x prime. These are just a little bit different. So if I want ax plus something, e to the t, to be equal to this, I get x prime equals 2, 3 e to the t plus 2, 1, 1 t e to the t plus, now what did I do here? I took 1 away from here, so I need to put that over here, and I added 1 to there, so I need to take 1 away over here, e to the t. And so this is equal to ax, where a is that square matrix, plus 1, negative 1, e to the t. So that, all off the camera. Sorry about that. I'll walk you back through it. So we have that matrix, the 2, negative 1, 3, negative 2 matrix, multiplied by our x is 2, 3 e to the t plus 2 times 1, 1 t e to the t. We also have x prime, which we found a few minutes ago, is this, and if we add it up, that's 3, 2 e to the t plus 2, 1, 1 t e to the t. So these almost match. This x prime is just a little different from our ax. So if I write it as ax plus something, what is that thing? Well, ax is 2, 3 e to the t. That piece is completely uncommon. So the difference between here and my x prime is this is 1 less. So in order for it to be equal to my x prime, I have to add 1. And this is 1 more. So for it to be equal to my x prime, I have to subtract 1. And so this is that extra piece in the original problem. And so we have verified that this x satisfies this equation, and that is a non-homogeneous first order system of equations, actually. So that gives you an idea of where we're going with this.